Hi, my name is Gabriel Dixon, and this is my video lab report for Lab 3. For this lab, we had two main objectives. First, determine the net forces acting upon our star, and second, determine the unknown mass of the black hole at the center of our orbit. Also, we will discuss the difference between the net force and the rate of change of momentum of an object, and if we could tell the difference between two different black holes that result in the same interactions with our model star. In the scenario for this lab, we have a star of known mass orbiting a black hole of unknown mass. Using the position versus time data of our star's orbit, we are tasked with calculating the mass of the black hole that our star orbits. Within this model, we are assuming that the gravity is the only force that is acting on our system. Rather than predicting motion like in the previous lab, we are using known movements to determine key factors that determine how these objects interact. Within the initial conditions of our code, we had to make a few changes. First, we need to update the mass of our star with its known mass of 2 × 10⁻³ kilograms. Then, we need to update our time jump, or delta t. Because we are told our data is given to us in intervals of a single Earth day, we need to convert 1 day into seconds, which gives us 86,400 seconds. Our next job is to edit the calculation loop to reflect our rate of change of momentum for our star. To do this, we first need to find our initial and final velocities. We can do this by multiplying our star's mass by its initial and final velocities respectively. Then, to calculate dB dt, we subtract the initial momentum from the final momentum and then divide that difference by delta t. This will give us our dB dt, and because they are equivalent, also our F net. Next, we will attempt to calculate the parallel and perpendicular components of our net force. The parallel component of our net force is the change in magnitude of our momentum of our object over the course of our time step. To find this, subtract the magnitude of our initial momentum from the magnitude of our final momentum and divide by delta t. After we find our parallel component, finding the perpendicular component becomes much easier. Because F net is equal to the sum of its parallel and perpendicular components, we can just subtract our parallel component from F net and find our perpendicular component. We can now use our calculations in Newton's universal law of gravitation to determine the mass of our black hole. We can rearrange the equation for gravitational force to solve for the mass of our black hole. Each iteration of our time jumps gives a slightly different mass, so an average needs to be calculated. From running our model, we found that our net force acting upon our star was 7.91914 times 10 to the 28 newtons. Then, our black hole's average mass was 3.31546 times 10 to the 21st kilograms. While in the real world, our black hole's mass should be constant, we found varying values for its mass when running our calculations. Our final mass was an average of all the different masses we found. This shows that our model is not infallible and that more accurate data could be obtained. For this experiment, how do the parallel and perpendicular components of the rate of change of momentum and net force differ? The answer is that they don't. According to Newton's second law, the net forces acting on an object are equal to the rate of change of momentum for that object. Thus, the parallel and perpendicular components of both are equal. Another question we might ask is, would we be able to tell if our mystery black hole was replaced by a black hole that mirrored the effects of our original? No. If the black hole doesn't lead to any changes in the original motion of our object, there is no way to tell because we can't observe black holes directly. All of our knowledge of black holes comes from the observations of their interactions with the surrounding bodies. So if those interactions are the same, there is no way to tell if our black hole has been substituted.